I was planning on giving you a quiz today, but after talking with a few of you, some things may not be entirely clear or be jiving right, so I thought I'd explain some things in a different way, and maybe it'd help get things more settled in your minds. For multiplexers and demultiplexers, the basic concept that you're dealing with is a data selector. Which is simply an AND gate. All right. So when you have the so when the select is low, doesn't matter what A is, Q is going to be 0. When select is high, Q follows A. Because it's a simple AND gate. If the select is low, any value is going ANDed with low is going to be low. Whereas if any value ANDed with high is going to be that original value. So with a multiplexer, you just have, say, 4. And you have 2 selection lines. You have, for A, which is your 0, 0 channel, select is going to be 0, 0. So you're going to have not S0 and not S1 ANDed together with, and that's going to be your select, going to select that output. For B, select, it would be 0, 1. So it would be S0 and not S1. Creating your selection for the data selector for B. For C, select is going to be 1, 0. So it'll be S1 and not S0. All right, and then finally D select is going to be 1, 1. So it'll be S0 and S1 ANDed together to be the selection for that AND gate. And let's do the necessary dots here. And here. So you have the the simple data selector here, here, and here. And these just provide the logic for the data selector. And then these are all ORed together, because only one of them is going to be, the possibility is going to be high. Is that a little bit more clear than the bowl of spaghetti that I presented on the board last time? Doing it with the separating it out into AND gates here, and then the data selector separate is maybe easier, make it easier to conceptualize. Yeah. If one person can't take it to the and those. Yes. You could graphically put all this in one 3-input AND gate, but I thought presenting it this way would be a little bit easier to visualize what's going on, how and why it's working. So yeah, that's the data selector at work. And the data selector is just simply the AND gate. So the state table for this would be S0, S0, S1, A, B, and C, and D, and Q. So you'd have 0, 0, 1, 1, 0, 1, 0, 1, and you don't really need the A, B, or C and D. You just need the Q. Q is A, B, C, or D. But that's the way the data selector works. and the decoder is just a subset of this. The decoder is a 2 to 4 decoder is just this. So your 2 inputs, S and O, SO and S1, select one of 4 outputs. So this could be drawn theoretically with a decoder here, with the input, with the outputs ANDed with the data selectors for each data select input, data input that is to be selected, and then OR that all together. Is this a little bit more clear? I'm introducing the new color blue to help with the, so as to avoid confusion on the diagram. But is that acknowledgement somewhere? Is that, yeah? I'm sorry, say that again?
Well, finding out the ones to click, depending on like the input combination which is one. But I'm a bit confused as to like how the good connection is very good.
Oh, that's S0 and S1? S0 and for C, S0 would be 0 and S1 would be 1 is the combination you're looking for. So S0 would be 0, which would be inverted to make it a 1. And then S1 would not be inverted to activate this AND gate. Yes, this is a multiplexer. Sorry, I didn't put that up here. And this is here. This here is a decoder, and this is a data selector. What's surrounded by this dotted line here is a decoder. It decodes the selection inputs into one of 4 outputs, which are then used to select which input is active on the output. All right.
The first thing we have earlier we have a select and
Mm-hmm. Yeah. Oh, it's just a select and Q 0 0 1. I'll do it. And it's just basically a AND gate truth table with slightly different labeling. And because it doesn't matter what A is, if select is 0, Q is going to be 0. Because that's the AND gate and truth table, right? So on the previous one, I just put I don't X for I don't care for A when the select is 0. So it's the same either way. Yes, this is the data selector truth table. So anything else not entirely clear, or do people seem to be getting it? All right. That well, let's see here. Want me to go over multipliers again? Multipliers? Okay. I'll go back a little bit further here. Let me get rid of this. All right. All right. All right. Now, multiplier, let's look at just 2 bits. 1, 0 times 1, 1. Okay. 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 1 is 1. Right? And then you add these together. This is basic elementary school math. Right? Okay, just with 1s and 0s instead of 0 through 9. So you have, this is A1, A0, B1, B0. Your two-bit numbers. So multiplication with binary numbers is done by the AND gate. A, B, let's call it P product 0, 0, 0, 1. It's multiplication. When you have Boolean expressions, you use a multiplication symbol to represent the AND gate, because that's all it is binary multiplication. So you do on the first in the first line, you do B0 times A0, right? So A0 to B0 in an AND gate. Okay? Then you'd have B0 times A1 in an AND gate. That gives you this first, what's called a partial product. All right. The next line is shifted over 1 because the second bit of B, B1, is shifted over 1 in the problem. So you shift it over. 1 times 0 is 0. 1 times 1 is 1. So you do A0, B1, multiply that together, and then A1, B1, multiply those together with an AND gate. Now you do your addition. Your rightmost bit is in the partial products. Doesn't do anything. It just goes. You don't add it to anything. So it goes straight down. That's your P0. You need to, in the second column, you need to start adding things together. So you do, in this case, you only have 2 inputs, 2 bits to be added together. So you can use a half adder. And the sum is your P1 and your carry goes to your next column, which it would need to be, if this were a 1 here, you would have to carry the 1 up here, because 1 plus 1 would be 0, 1. So you'd have to carry the 1 and add it to the third column. And because, again, you only have 2 inputs, you could use a half adder here as well. And that's going to be your P2. And your carry is going to be your P3. So it's just a matter of getting your partial products with AND gates, and then adding your partial products together using adders. either half adders or full adders, depending on how many bits you're going to need. You're adding together. With a 3-bit by a 3-bit multiplied by a 3-bit, you would need full adders in there as well, because carrying and adding more than 2 bits. But so there's your basic 2-bit multiplier. Yeah. Is that a little bit more clear than I explained it last time? First time teaching the course. I don't claim to be perfect or experienced in this, in explaining things, but I am willing to listen and re-explain if things are not clear. But yeah. Now, the subtractor might have caused a little bit of confusion. How to make a adder into a subtractor? Did that need to be readdressed? All right. So we know that subtraction is just adding a negative number. And a negative number is represented in binary using 2's complement. So when you have a sequence of full adders, let's say 4 bits, and you have A3, A2, A1, A0, B0, B1, B2, and B3. All right. So that would just give you your sum, just as this is. I gave you your that would give you your sum of the 2 bits if you're just adding. Oh, forgot the carries between the full adders. Okay, so how do you go back to the first section of the course? How do you make a binary number negative? I'm sorry? And add 1 after you do what? Flip the bits. Exactly. So we conveniently have A XOR B. Well, let me do, to avoid confusion here, XY X XOR Y. All right, we got 0 0 or 0 1. Can't write. 1 1 0. So what we can derive from this is if x is 1, if x is 1, the result is the inverse of y, right? If x is 0, the result is equal to y. So x XOR 1 equals x prime. Or actually, let me put that in terms of y, because that's what I... Okay? And y XOR 0 equals y. Okay? So to invert b over here, we can use a exclusive OR gate at each input to the full adders and put a 1 there. And if we're not inverting it, put a 1 in the other input of the XOR gate. So you put the XOR gate here, and then put all these to 1 if you want to invert it. And call that your subtraction line. Subtraction select. All right. But inverting the bits isn't the whole story. Like he said, you add 1 to the add 1. So you run the selection line into the carry in of your first full adder. That adds 1 to the B argument. So you use a exclusive OR gate as a selective inverter. That's how you make a adder subtractor combination. Does that make sense? It does both. If sub select is 0, it's addition. If a subselect is 1, it's subtraction. Make sense?
Can you like go back how this
Oh, when you're when the subtraction select is 1, the exclusive OR gates are all going to be acting as inverters, because one and the other, one XORed with the other input inverts the other input. Okay? When it's 0, it doesn't invert the input, and the full adders just do simple addition. The full adders do simple addition either way. It's just one's with a negative number and one's with a positive number. So, is that a little bit more clear, or not quite?
what's inputs are 0 and 1?
On the subtraction select? The subtraction select, this line right here. That right here. It's like a function select. If it's a subtraction, if it's a 0, it's regular addition, and if it's a 1, it's subtraction. Invert plus 1.
Can you explain how the people how you got the y and
Yeah, if y exclusive OR with 1, so y exclusive OR with 1 is going to be the inversion of y. See? Whereas if I don't have a third color, well, I do have a third color. Whereas with green, if you're exclusive ORing y with 0, your result, the result matches y. But if it's a 1, the result is the inverse of y. Yep. Yeah. Just like it would be if you were to run it through an inverter. It's a selective inverter. So, any other questions? Don't have enough time to go over much else, but we'll have a quiz or test or whatever you want to call it on Friday on these topics. So please be here, and I will see you later. Have a good day.